Hello, my name is Magnus Petersen, and this is my tutorial number 18 on TensorFlow, and this is about the TFRecords binary file format and the Dataset API for TensorFlow. It took several days to figure out how to use this because the official material, once again, was very difficult to understand, and there's really not much official information on how to convert, for example, images to TFRecords. There is this small Python script made by the Google developers, but there's not a lot of comments in the code. Actually, I don't think there's no comments in the code. And I will get back to this in a moment because it is actually not very well made and you don't understand what is going on. So it's also difficult for you to modify it if you have datasets that are very different from what you're converting here. And this is the official tutorial on using the Dataset API. And I found this to be very abstract. And I found a tutorial on YouTube made in Chinese that I thought was easier to understand than this. Then there's a blog post, and I believe I also showed this in the last tutorial on the Estimator API, and this blog post is not bad, but it doesn't use TFRecords, so it doesn't do exactly what we want. So it took me several days to figure out how to actually do this, even though when you see it, it's not that many lines of code, but it's difficult to understand, especially because the API is not very well designed and it's not very well documented. So you have to read on Stack Overflow and blog posts from high school kids and whatever in order to gradually piece together how to do it. And when you have weird errors, it can take a long time to figure out how to solve it. So this tutorial builds on number 17 on the Estimator API, and what we will show here is how to convert a dataset with images into TFRecords, and then how to use the Dataset API with the Estimator API to use this dataset during training and testing. So far, we have been using what is called the feed dict, and that is a fairly easy way of inputting data to the TensorFlow graph. The problem is that it's a huge performance bottleneck because we have to read some data using Python, then we perform an optimization step, then we loop back and have to read some more data, then another optimization step, and so forth. And this means that the GPU is always waiting for data. And in some of the previous tutorials, I have tested it with a GPU, and the efficiency might only be 50% or may even only be 30% of the GPU because it's always waiting for data. So we want to be able to load data in a parallel thread so it's always ready when the GPU needs it. So once again, we need a bunch of imports, and the Dataset API is now included in TensorFlow Core, but we also need this helper function for reading and converting images from, for example, JPEG files to NumPy arrays, and then we need a few other things for printing progress and various other things. So the dataset we're going to be using here is called Knifey Spoony, and it is a dataset that we created in tutorial number 9, and it has already defined all the integer constants that we will be using, such as the size of the image and the number of classes and so forth. And if you want the dataset placed in another directory, you write it here, and then we can automatically download and extract it. And then we can load the dataset, and then we have the class names here, Forky, Knifey, and Spoony, and if you're not familiar with this, it will become apparent in a moment what this means. This dataset does not actually load the images into memory, even though there's not that many, but it loads the path names of all the images, and we have the class numbers as integers, and we have them as one-hot encoded labels. So we get a whole array of file paths like this. And we get the same for the test set here, and we have an example of a path here as well. The training set contains 4,170 images over 3 different classes, and the test set only contains 530 images. And these are images that I made from video recordings in tutorial number 9. And here we have a helper function for plotting images. And because the images are not actually loaded, we need a helper function for that. And we just use the helper function from matplotlib like so. And then we can plot a few of the images to see if the data is correct. So these are all images of knives, forks, and spoons. And it's an old Simpson joke, and you can look it up on YouTube about the knifey spoony. But we essentially want to classify whether an image shows a knife, a spoon, or a fork. Okay, so now we want to convert the Knifey Spoony dataset into a highly efficient binary file format that can be read by TensorFlow. And this is called TFRecords, which is supported inside TensorFlow. And if you have a very large dataset, you would normally split the files so they don't become too large. This also has the advantage that when you are shuffling or randomizing the data when you read it for the training of the TensorFlow graph, the randomization becomes a lot better because it does not read the whole file at once into RAM. It only reads a small buffer. So if we read buffers from 10 or 100 TFRecords files, then the shuffling becomes a lot better. But our file is very small, so I've made it an exercise that you modify the code so it can split it into multiple files, which are also called shards. So this is the path for the TFRecords file for the training set. And here we have the path for the test set. And here we have a short helper function for printing the progress during the conversion. And this is why we needed the sys import. And here we have two helper functions for wrapping data. This is for an integer, and this is for an array of bytes. And I believe you can also use an array of integers up here. But again, this is not documented properly. And you see this is super complicated. tftrain.feature, and then we have to nest it with a tftrain.int64 list. And then we have to wrap the value in a list. And you really wonder what it is that it's actually doing. And this is what it looks like inside the TensorFlow code. So you have no idea what this means. Absolutely none. So anyway, we have these two wrapper functions, which we are going to use in this conversion function. So it takes a list of path names for the images as an argument, and it takes the class labels as integers or as one-hot encoded arrays, and then it takes a file path for the TFRecords file that we want to output. And the essential part is that we have to open this TFRecord writer, and then we have to iterate over all the image paths, and then we load the image using the helper function from matplotlib, and then we convert it to raw bytes, and then we create a dict where we wrap the bytes and we wrap the label using the helper functions that we made above. And then we wrap this dict in a tftrain.features. And then we wrap this again in an example object. Then we serialize the data. And then finally rewrite it to the TFRecords file. What does all this mean? I'm not exactly sure. Again, it is poorly documented, and if we go back to the source code that the Google developers have actually provided, this is more or less the same that we are doing in my version of this code. But here you will see that the last 4 function calls are here, and they are actually nested. And I think that the design philosophy, if you want to call it that, is that 1 function call is good, so 4 function calls must be 4 times as good. And if we nest the function calls, then it's exponential goodness. So it is turtle nerdgasm. Of course, the reality is that this API is poorly designed, and it's also a very bad idea to nest complicated function calls like this, because it's so much harder to understand than if you unroll the function calls like I have done here. But the question is, why do we need 4? Because every time you want to call this writer.write, I think you have to call these 3 as well. So why are these 3 function calls not internal inside this write function here? This is one of the aspects where TFRecords looks like it's kind of an alpha or beta API. It's really not finished, it is unpolished and could have been much better. Anyway, we then call the convert function we just made with the list of path names for the training set and the class numbers as integers because we want to save integers rather than one-hot encoded arrays into the TFRecords file. And then we have the path name for the output file, and we do the same for the test set. And we can then open a terminal window, and we can use this xxd command to see the binary contents of the training set. And it looks like this, and this, and this, and so forth. And we can also see how large the files are, and the training set is now 478 megabytes, and the test set is 61 megabytes. And compare that to the size of the images on the disk, and this is maybe, I don't know, let's say 30 megabytes or something like that. So the TFRecords files are absolutely enormous compared to the original JPEG files on the disk. If we go back and look at the conversion function, the problem is that we are decoding the JPEG files in this line here using the helper function from matplotlib, and we are storing the decoded raw bytes into the TFRecords file. And these images are, I believe they're 200 by 200 pixels, 3 color channels, and 1 byte for each pixel per channel. So these images are actually quite large. You can also store the compressed JPEG files in the TF-record file because this wrapper function here takes any bytes you like. So we can just load the JPEG file as bytes, store it in the TF-record file as bytes, but then we have to make an appropriate decoding when we read the file later in the so-called parsing function, which you will see below. And this is an exercise, and you can try and see if you can get that working, so you can find out what the pros and cons are of both ways of making these TF-records files. Okay, so now we have made the TF-records files, and we will now modify the code from tutorial number 17 on the Estimator API so that we can read these TF-records files. To do that, we need the so-called parse function, because you have to remember that the TF-records files contains binary serialized data. So we have to decode or unpack this data again. And first we define a dict with the data names and the types that we expect to see in the TF-records files. And once again, I think the TF-records format could have been made better, because this could probably have been written in a header, so we didn't have to make this again. It's a little awkward that we had to define it when we make the file, and now we have to define it again when we want to read the file. So anyway, we call this tf.parse single example with the serialized data and the features that we expect to see in the TF-records file, and we get a dict out of that, and then we can take the field with the name image, and this gives us the raw bytes that we have written into the TF-records, which we then have to decode, so we get unsigned 8-bit integers out, which we can then cast to floating point, because that is what we need to input to the TensorFlow graph. We can also get the label, and then we return the image and the label. So this is just a parse function that we will have to use somewhere in the input pipeline. So here we have a helper function for creating the input function that the Estimator API needs for reading the TF-records files. So we have this input function for both the training set and the test set, where we will then change the arguments here. So the first one is the file name for the TF-records file, and then we have a boolean whether this is for the training set or the test set, and this is how large a batch size we want to return, and this is the buffer size that we will use for random shuffling of the data. And then we create the object from the Dataset API that is capable of reading and shuffling data from a TF-record file. And we can then chain various modifications onto this dataset object. The first one is the parsing. So when we read the raw data from the TF-records, we first have to unpack or decode this data using the parse function that we just made above. Then if we are reading the training set, then we also want to shuffle it, and we will allow for infinite reading of the data, so we can repeat the dataset an infinite number of times. If instead we want to read the test set, then we don't shuffle the data and we only repeat the dataset once. And then we chain this repeating onto the dataset like so, and we get the batch like so. And then we have to make an iterator, and we have to get the next batch of images and labels. And because the Estimator API expects the input to the model to be a dict, we have to just wrap the image batch like so, and then we can return it. And once again, this is somewhat complicated. Could this have been made simpler? Maybe it could. And then we have two small helper functions, because the Estimator API expects the input functions to have no arguments. So we just set the relevant arguments here for the training set and for the test set. One of the questions that I have gotten a lot on some of the other tutorials is how do people load and input their own images? So I'll show you how to do that here, and we actually just use the code from the previous tutorial. So we first need to load the images using the helper function that we had made above. Then we have it as a NumPy array, but we need to cast it as floating point because that is what the TensorFlow graph will expect to see. And then we use this NumPy input function to wrap this NumPy data so it can be input to the Estimator API. So if you want to load other images, you just do it here, in this line here. And when we are running predictions on the Estimator API, we don't need the true class number, but when we want to plot these images below, we will need the class number, so we take it here. So now let's see how we use this dataset with a pre-made or canned estimator. And I believe this code is exactly the same as in the previous tutorial, probably except for this here, where we had named the input feature X in the previous tutorial, but now it's named image, because it has to match what we are returning from the input function above. And if we go back, you will see that we named it image in this dict here. So what we are getting out here is what will be input to the Estimator API. Alright, so if you have more than one input feature, you can combine them in a list. And we want to make a fully connected neural network with this number of hidden units in the layers. And we do it like this. And I have also changed the directory for the checkpoint file, but otherwise it's the same as in the previous tutorial. And we can then train it, and this is much slower than in the previous tutorial because these input images are quite high resolution compared to MNIST. I believe MNIST is 28 by 28 pixels for a grayscale channel, while we have 200 by 200 pixels for 3 color channels. So these images are much larger, which means that the fully connected neural network is also much larger. It has many more weights that need to be optimized. So we only run 200 steps. And then we run the evaluation using just the same code as we had in the previous tutorial, because this is now independent of the dataset as long as we have this input function for the test set. And what we get out is a classification accuracy of 45.66%, which is very bad, but it actually gets worse, as you will see in a moment. Because if we run predictions on the 10 images that we had loaded from the test set using this predict input function, you see that it has classified all these images as spoony, while they were all forky. And I wondered whether it had done this for the entire test set, so I wanted to get the predictions for the entire test set, and we do that simply by calling the same predict function, but we use the other input function for the test set instead of for the small sample of images in the predict input function. So what we get out is that it has predicted the class number 2 for all the images in the test set. I count them here, and there are 530 for which the predicted class is 2. And as you may recall, the dataset contains only 530 images in the test set. So our model has predicted that all images in the test set are class 2, which is a spoon. So it is completely useless for this dataset. And I actually thought that this was not very good for demonstration purposes, because this might indicate that there's another problem somewhere in the code. Maybe I had a bug when I loaded the code or whatever. But let's try and make a convolutional neural network instead and see what we get. So you may recall from the previous tutorial that we have to make this model function, and I was not too happy with this because you have to do a lot of things inside this model function. But in this example, it is actually more or less the same as in the previous tutorial. Again, we have to change the name here in the features for image instead of an X, and I have just changed these convolutional layers a tiny bit from the previous tutorial. Otherwise, it is the same, and it looks like this. And the code for creating an instance of the estimator is also the same, and it looks like this. And we train it in just the same way, like so. And we can evaluate its performance on the test set in the same way again. And we get a classification accuracy of 39.06%. And this is actually worse than for the fully connected model we had made above, which couldn't classify at all. It had just said that all the images are spoons. So let's look at some predictions again. But this convolutional neural network has predicted that the images in this small sample batch here are all forks, which happen to be correct. So let's try and run the prediction on the entire test set. And again, we just have to use the input function for the test set. And we now get out all these predicted class numbers. And you will see they are different. So we have 0, 1s, and 2s. And we can count them, and we see that we have 333 classifications as 0, 144 images were classified as 1, and 53 images were classified as 2. So the accuracy is still absolutely horrible, but it is an exercise that you can try and run this training on the convolutional neural network for much longer. You could try and run it, for example, for a whole night using a GPU and see if it actually can start to learn it. I'm not sure that it can. I actually haven't run this. So this dataset was not great for demonstration purposes, but hopefully the code is actually correct and you can use this code with another dataset. So this tutorial showed how to convert image files into the binary file format for TensorFlow called TFRecords, and to use this with the dataset and estimator APIs. And this simplifies the process of training models with very large datasets, and also ensures that you get very high usage of the GPU, because it's now very efficient input pipeline for the TensorFlow graph. And it doesn't take that many lines of source code, but the API is a bit awkward, and it could have been made much simpler in certain ways that I also discussed in the previous tutorial. And I think the way that you're probably going to use this is you're just going to copy and paste code from this tutorial or somewhere else else, and then you modify it for your own needs, and then in your next project you copy and paste that again, but maybe you never fully understand what the code is actually doing, and that is because the API is not super polished. I wish it would have been simpler and easier to understand. And as always, you can click on the link below the video to download the source code.